All right, welcome everyone. Let's jump right into an explainer that completely rethinks how we measure statistical data. Look, if you work with data, you know that the tools we use entirely dictate the truth we see. Well, today, we're looking at a truly revolutionary approach that challenges the very foundation of traditional hypothesis testing. I want you to think about your own work for a second. Have you ever had a massive sample size flag a completely trivial difference as statistically significant? Or maybe you felt that universal, crushing frustration of relying on fragile, confusing p-values that completely ignore statistical power. We have all been there. You run your analysis, you cross your fingers, and bam, a tiny, essentially meaningless effect size throws a significant p-value purely because you have thousands of data points. It's a known, incredibly frustrating flaw in the traditional system.
Section 1. The p-value problem and the entrenched champion.
So, let's explore exactly why researchers are desperately seeking a better statistical tool than our reigning champion, the p-value. It's everywhere, sure, but it's widely misinterpreted, it's heavily sensitive to sample size, and frankly, it doesn't inherently reflect the actual power of your test. To understand this shift, we really need to compare this old guard with the new. Unlike the traditional t-test, which basically forces your data into a perfect theoretical bell curve box, assuming equal variances and perfect normality, NNS AOV, which stands for Nonlinear Nonparametric Statistics, is completely agnostic. It literally doesn't care if your real-world data is skewed, weird, or just packed with outliers. It steps back and lets the data speak for itself.
Section 2. Meet NNS ANOVA certainty.
So what's the actual fix here?
Enter our new hero metric, the certainty statistic. We're transitioning to a revolutionary new framework designed specifically to fix the p-value's biggest flaws. Instead of some binary, confusing p-value threshold, NNS gives us an incredibly intuitive 0 to 1 scale, essentially a 0 to 100% certainty scale. It's calculated based on the squared deviations from the null hypothesis adjusted for your sample size. Simply put, it tells you the actual likelihood that your samples share the same population mean or distribution. A 0.96 means you are 96% certain they're from the same population. It's just brilliant in its absolute clarity.
Now, the engine running this certainty statistic is something called the lower partial moment CDF, or LPM.1.CDF. I know, it sounds a bit intimidating, but think of it this way. Instead of the jagged, step-like charts used in older methods, this creates a smooth S-curve based on area probabilities. That smoothness, that's your shock absorber against noise. This is absolutely crucial because it significantly stabilizes the data, especially in small samples, and it helps you completely avoid that trap of sample size sensitivity, where massive datasets falsely flag trivial differences. And you know what the best part is? NNS ANOVA isn't just a one-trick pony. It's a versatile toolkit that gives you 3 distinct modes of operation. First, the means mode, for testing pure mean differences. Second, the full distribution mode, which uses quantiles to test the entire shape and variance of the data. And third, the medians mode, which zeroes right in on central tendency. This gives researchers total control. For instance, if you're analyzing income data, which, as we know, is famously skewed by outliers, you'd use the medians mode. Why? To test what the actual average person makes, without the whole thing getting distorted by a handful of billionaires. It lets you test exactly what matters.
Section 3. The Gauntlet. Surviving the Edge Cases. Okay, let's dive into this and put this tool through a high-stakes obstacle course of 4 brutal data edge cases. We want to prove its empirical superiority against the t-test, the Kolmogorov-Smirnov test, and Kruskal-Wallis. In our first test, imagine comparing a dataset with 2 massive peaks, bimodal data, against a simple bell curve. They actually share the exact same center mean and median of 0. Well, the traditional KS test completely panics. It gets totally distracted by the shape and throws a highly significant p-value of 5.42 e to the negative 8, loudly rejecting any similarity. But look at NNS median's mode. It delivers a 0.974 certainty. It perfectly identifies the shared central tendency without getting confused by the spread.
Now look at what happens in our second case, log normal skew. Here, we've got a highly skewed log normal distribution matched against a standard normal one with a similar mean. The t-test entirely misses the massive tail of the skewed data. It gives us a p-value of 0.836, basically shrugging and saying there's no difference. But NNS full mode catches it beautifully.
Because it evaluates quantiles, it instantly recognizes the shape divergence, and the certainty properly drops to 0.730. It's balanced, it's nuanced, and it is power-informed.
So the absolutely crucial point here is this shocking number, 1.62 e to the negative 11. That is how wildly the traditional t-test overreacted when we fed it dependent time series data. Think of an AR1 process like daily weather or stock prices, right? Where today's data heavily depends on yesterday's. Traditional tests assume every single data point is entirely independent. So when they see this kind of data, they freak out and throw extreme false positives.
Let's look at the full time series results. Because the t-test, the KS test, and Kroskal-Wallis all rigidly assume independent and identically distributed data, they completely over-reject the similarity here. But NNS has this built-in robust permutation feature. By toggling this on, NNS cuts right through that autocorrelation noise like a hot knife through butter and provides a cautious, power-informed certainty of 0.532. It sees the slight mean shift, but it absolutely doesn't overreact to the dependent nature of the data. Now, check out this number, 0.974 certainty. No way, right? This is the score NNS achieved when we purposefully injected 10 extreme, massive outliers into a standard normal distribution.
When we look at the results, the resilience of NNS becomes crystal clear in this final gauntlet. While the t-test gets completely derailed by those 10 outliers, artificially pulling the mean and giving a significant p-value of 0.031, the KS test acted super weird too, providing an erratic 0.466, but NNS medians? It robustly ignored all that noise. It recognized that the core median of the population actually hadn't changed at all, delivering a stable, highly accurate 0.974 certainty. Section 4, the verdict. A viable replacement?
Okay, so we've seen it handle identical means with different shapes, heavy skew, time series dependency, and extreme outliers. Literally the whole shebang. So looking at the empirical proof across all these edge cases, 3 distinct victories emerge for NNS. First off, intuitive clarity. A 0 to 1 certainty scale is just infinitely more understandable than an arbitrary significance threshold. Second, high stability. Thanks to that smooth LPM curve and robust permutations, it effortlessly handles non-IID data and outliers without falling apart. And finally, it is power-informed. Unlike p-values, the NNS certainty statistic actually correlates strongly with test power. This solves the exact frustration we talked about at the very beginning of this explainer. It delivers clear, stable, and power-informed results across the board without ever relying on rigid assumptions.
Well, that brings us to the end of this explainer, and I want to leave you with a question to ponder. The evidence is right here. The old methods are fragile, and they are easily fooled by messy, real-world data. So the question is, in your next dataset, are you going to cling to arbitrary significance, or are you ready to upgrade to measurable, intuitive certainty? It might just be time to leave the flawed p-value in the past and embrace a much more certain future. Thanks for tuning in.